Welcome back, everybody. In this video, we're going to be continuing with section 4.1 by looking more at compound interest. So in the last video, where we'd ended was we had developed a formula for calculating compound interest. P was the amount of principal, R is the interest rate, N is the number of compounding periods per year, and then T is the number of years. And the formula was P, and then in parentheses, 1 plus R over N, and then in the exponent, both the factors N and T, so N times T in the exponent. So we're going to try one more example. So here we have $6,000. It's invested at 3.22% interest compounded daily. We want to find the value after 8 years. So you may want to pause the video, try this on your own, and then make sure that you can get the right answer. We'll go through it together. So let's see what we got. So the future value is what we want. The principal is 6,000. It's going to be invested at 3.22%, which is 0.0322 as a decimal. And then the compounding frequency is daily, so there are 365 days in a year. And then for the exponent, it's 365 days for 8 years. Okay, so 365 times 8. All right, so then let me type that up. We'll see what we get. For monetary amounts, it's a good idea to round your final answer to the nearest cent, because that's what we use, unless the instructions for the problem tell you to round to something else, like dollars or something else. But I would round to the nearest cent if you don't have any other advice. All right, so we get 7,762.84. Okay, when you are entering some of this stuff into your calculator, you want to be really careful how you type it in, especially with exponents. For example, let's say you wanted 2 raised to the 3 times 2 power. 3 times 2 is 6, right? 2 to the 6th power is 64. So this is the answer that you should get. Just 64. If you type in just 2 and then like this caret or up arrow for power and then 3 times 2, the computer is going, or calculator is going to just follow literally order of operations and do exponents first. So the calculator would read this as 2 cubed times 2, or 8 times 2, or 16. In order for it to keep both the 3 and the 2 in the exponent, you need to wrap it in parentheses, as is done over here on the right. So be very careful about that. Or for a problem like we just did with a compound interest, figure out 365 times 8 first, write that down, and then type in like all the rest of it. For the part inside of parentheses, it worked out on this one to be 1 plus, it was 1 point, a whole mess of zeros, and then 882. I would try to keep that in your calculator. Don't round that before raising it up to a power, because it's going to end up introducing errors, and you'll end up getting the wrong answer. So try to keep this part in parentheses just in your calculator without having to write it down. Otherwise, you're going to lose digits. Okay. All right. The next part is about the number e, which is called the natural exponential base. We saw when we did our first example about the $1,000 at 10% for 3 years, that if we increase the compounding frequency, that the dollar amount that we get would increase, but by less and less each time. And so it approaches what's called a limiting value that you would learn more about in calculus, but for now we'll leave that go. It approaches what's called a limiting value. And so that's related to this number e. So this number e is an irrational, it's actually a transcendental number, kind of like pi is. And it represents the value that 1 plus 1 over n raised to the n power gets closer and closer to as n increases without bound. And you can see that in this table kind of towards you, right? Putting in different values of n, we get a decimal that's closer and closer to 2.71828. And like pi, it's not a number where we know it exactly. We have to use decimal approximations for it always. but it is basically the kind of ending or limiting value of this expression, 1 plus 1 over n raised to the n power. If you have a scientific calculator, it should have an E button on it. That number E is called the natural exponential base, and it's also called Euler's number, after a German mathematician named Euler. It looks like it should be pronounced Euler, but since it's in German, it's pronounced a little differently. EU for Euler. Okay, the natural exponential function is f of x equal to e to the x. It's a increasing exponential function. It passes through the points 0, 1, and 1e, has domain all real numbers, and then range 0 to infinity. Okay, so we'll use that here in a few examples. Okay, I wanted to include just this one example. This one is taken from a completely different math class, just to illustrate how that natural exponential function can be used. This one is actually got a lot more to it than that. This one is 1,000 minus 1,000 e raised to the minus 0.01 times x, and that's shown graphed here. And it turns out that this function represents the solution to this problem shown here. You don't need to be able to solve this problem in this class. I just want to just show you an example of a physical situation that ended up involving that letter E in its solution. If you go on to take a lot more math or some certain science classes, you will perhaps run across problems like this again. Okay, all right. Okay, so out of all of the different exponential bases you can have, we will have occasion to use the natural exponential base. And so that's what this slide is about. It's about the continuous growth or decay formula. And so we saw that we could calculate the compounding or calculate compound interest or compound growth at regular intervals. If we increase the compounding frequency without bound, we get what's called a continuous growth or decay formula. And the formula goes like this. A of t is a times e raised to the rt power. You can contrast this to the f of t is equal to ae. All right, this formula that we had before, f of t is ae to the, sorry, that was not the one that we had had. We had had ab to the x before, sorry. Too many formulas. All right, so f of x is ab to the x was a prior formula that we had had. The base was b, the initial value was a. If we use e as our base, then frequently we'll do that. The r is the growth rate shown in this formula. A is still the initial value. Here they've used the t for the independent variable because frequently these are functions of time. So here A is the initial value, R is the continuous growth rate per unit time, T is the elapsed time. If R is greater than 0, then this model would represent growth. If it's negative, then it would represent decay. Okay, for business applications, we use the continuous growth formula for continuous compounding of money. And so the formula looks like this, P times E raised to the RT power. So instead of A for initial amount, they'll use P for principal in the context of money. But the concept, the growth concept is basically the same. All right, so as an example, going back to our $1,000, suppose that we invest that $1,000 at 10% interest for 3 years, but do the compounding continuously. We want to find the future value of that investment. So A is P-E-R-T. Good idea to rewrite the formula each time you use it until you get the formula memorized. So it was 1,000. And then E raised to the 0.10 times 3. Okay, so then you should have a button on your calculator that has E in it. If you want to find it, it'll probably be paired with a natural logarithm button. We will learn more about that later. It's probably shifted, so maybe the ln is on the face of the key and e to the x is shifted, or perhaps it's the other way around. the e to the x is on the base of the key and the ln is shifted, but you should have one of those. All right, so let me type that into my calculator and let you know what we get. Try to find mine. There we go. All right, so that worked out to be $1,349.86 using continuous compounding. We have another example. So here, in order to have $10,000 in 5 years, we would like to know how much we should invest now at 6.75% annual interest compounded continuously. So on this one, instead of wanting to know what the future value is, this time we know the future value and we want to know how much we need to start out with so that we end up with this $10,000. So again, our formula, A is equal to PERT. And so we want to end up with 10,000. And P we don't know. The interest rate is 6.75%, which is 0.0675. And then this is going to be in 5 years. All right, so the e raised to that exponent is just a constant. And so we're going to divide by that. You can figure it out now. I'm going to wait to put it into my calculator just so I don't have to write down a bunch of decimals. All right, so here I've solved for P. So P is approximately. All right, so here this one worked out to be about $7,135.52. That's how much you would need to invest now at 6.75% annual interest compounded continuously in order to end up with $10,000 in 5 years. All right, so that takes us to the end of this part of the video. We will continue onward with some more examples here in the next part. Let me know if you have any questions and have a great day.